Ever wondered what the universe is made of? Why do particles behave the way they do? You're not alone. Scientists have been pondering these questions for centuries, and the best answers we've got so far are wrapped up in something called the Standard Model. Imagine the universe as a giant Lego set. The Standard Model is like the instruction manual, explaining how to put together the building blocks to create everything around us. These building blocks include particles like quarks, leptons, and bosons. It also includes the forces that hold these particles together or push them apart: gravity, electromagnetism, and the strong and weak nuclear forces. But here's the twist. Our Lego manual, the Standard Model, is missing a few pages. It brilliantly explains the behavior of most particles and forces, but there are some things it just can't account for. Dark matter, dark energy, the dominance of matter over antimatter in the universe, the Standard Model scratches its head at these. But the Standard Model isn't perfect, it doesn't explain everything. And that's where experiments like the CMS at CERN come in. This is the frontier of physics, where scientists are probing the universe's deepest mysteries. Stay tuned as we delve into these exciting experiments and their mind-bending implications. So what exactly is this CMS experiment that's causing such a stir, I hear you ask? Well, let's dive in and explore this fascinating world of particle physics. The CMS, or the Compact Muon Solenoid, is a high-energy physics experiment at CERN, the European Organization for Nuclear Research. It's one of the 4 main experiments at the Large Hadron Collider, the world's most powerful particle accelerator. Picture it as a giant microscope peering deep into the fundamental fabric of the universe. Now, the CMS experiment has a rather grand mission. It aims to validate the Standard Model, which is the theoretical framework that describes the fundamental particles and their interactions, but it doesn't stop there. It also seeks to venture into the uncharted territory of new physics beyond the Standard Model. It's a bit like trying to confirm if the map of our known universe is correct, while also looking for hidden continents. Recently, the CMS experiment made a significant stride in this mission. It precisely measured the effective leptonic electro-weak mixing angle. That's quite a mouthful, isn't it? But, in simpler terms, it's a key parameter in the Standard Model that deals with how particles interact with each other. The exciting part? The measurement aligns with the prediction of the Standard Model. It's like solving a cosmic jigsaw puzzle and finding that the pieces fit just as expected. But why is this precision measurement a big deal? Well, it's not just about confirming the Standard Model. It also opens the door to exploring new physics. It's a bit like using a magnifying glass to uncover hidden details in a masterpiece painting. The more precise the measurement, the more potential there is to uncover new insights into the universe. So, the CMS experiment is a bit like a cosmic detective, meticulously collecting clues about the fundamental nature of our universe. It's a complex task, akin to finding a needle in a haystack. But in this case, the needle is invisible and the haystack is the size of a galaxy. Now, isn't that an adventure worth embarking on? So, why should anyone care about this recent measurement? Well, let's break it down a bit. Imagine you're trying to assemble a complex jigsaw puzzle, but you're not entirely sure if you've got all the pieces. That's kind of what physicists are dealing with. The puzzle is the universe, and the pieces are the fundamental particles and forces described by the Standard Model of particle physics. This recent measurement is like finding a puzzle piece that fits perfectly. It's a precise measurement of the effective leptonic electro-weak mixing angle. Now, I know that sounds like a mouthful, but think of it as a key parameter that helps us understand how particles interact with each other. This measurement aligns with what the Standard Model predicts, giving us greater confidence that our understanding of the universe is on the right track. But it's not just about validating what we already know. It's also about exploring new possibilities. You see, by making these precise measurements at a hadron collider, we're opening up avenues for discovering new physics. That's like finding a hidden compartment in our jigsaw puzzle box, with even more pieces to play with. And then there's the matter of resolving discrepancies in previous measurements. This is like realizing some of the puzzle pieces we thought fit together actually don't. The recent measurement signifies a significant step towards clearing up these inconsistencies, which could ultimately lead to a more cohesive picture of our universe. So, if you ask me, that's a pretty big deal. It's not just about nerdy physicists getting excited over tiny particles, it's about piecing together the fundamental workings of the universe, one puzzle piece at a time. Basically, it's like proving your grandma's secret recipe is indeed the best, but you're using quantum physics and a massive particle accelerator. So, Where does this leave us in our understanding of the universe? Well, let's recap. We've explored the fundamentals of the Standard Model, a theory that describes the basic building blocks of the universe and how they interact. It's like the periodic table but for particles. Yet it doesn't have all the answers. Enter the CMS experiment at CERN, pushing boundaries and testing the Standard Model's limits. We've delved into the recent precise measurement of the effective leptonic electroweak mixing angle. Sounds like a mouthful, right? But this is no small feat. It's a significant stride towards resolving discrepancies in previous measurements and a shining example of the wonders of precision physics. What's the big deal? Well, every bit of data we collect helps us validate the Standard Model's parameters and explore new physics. We're not just crunching numbers here. We're attempting to understand the very fabric of the universe. We may not have all the answers, but with each experiment we're one step closer to understanding this cosmic mystery. So, next time you look up at the night sky, remember, there's more to it than meets the eye.